In this lesson, I'm going to talk about group structures, including topics such as cosets, normal groups, quotient groups, and homomorphisms and isomorphisms between groups. A basic concept used in the study of group structure is that of a coset. Given a subgroup H of a group G and an element A of G, which may or may not be an H, then the left coset AH is defined as the set of all multiples of A times the various elements of H. Sometimes you'll see a notation like this, not as often, but sometimes you'll see this where the star is the group operation. And if the group operation is addition, you'll see this notation, which in fact I use sometimes. So any one of these three notations could be used. And you can also do this on the right. That would be a right coset if you multiply by A on the right of H. Let's look at an example. Consider the group of integers under addition and the subgroup consisting of multiples of 3. This here, I'll leave it to the listener to prove that this is a subgroup. It's pretty easy, but you may want to go through the four properties to check that. And then there are only 3 distinct cosets of H. So we'll use the plus notation here since we're talking about addition. So you have 0 plus H, each element in H, and of course you just get H in that case. And then you have 1 plus each element, and you get this set of numbers. And then you have 2 plus that, all the elements in H, and you get these numbers. And then if you do 3, you're just going to get the same set again, and same 4 will give you this again, and 5 will give you this. So there's only 3 different cosets of this subgroup of G. The other thing to notice is that if you take all 3 of these together, you get everything that's in G. And that's general and true, not just for this example. We'll see that this is all the cosets taken together give you the containing group. For our second example, we're going to look at the symmetric group S3, which I've written out here. Each one of these terms are written in cycle format. So for example, this last one here says 1 gets mapped to 3, 3 gets mapped to 2, and 2 gets mapped to 1. And where you only have 2 elements, like say 1, 2, you have 1 mapped to 2, 2 mapped to 1, and then 3 just gets mapped to itself. And we want to look at the cosets, both left and right, of a subgroup. And the subgroup is this one here, the powers of 1, 3. So you have the identity, and then if you multiply 1 3 times itself, you just get the identity again. So there's just 2 elements in this subgroup. If we multiply on the left by each element in our group S3, I've shown the results here. We can just look at one in detail. Let's look at this one here. So you take 1, 2 times H, and of course 1, 2 times the identity is 1, 2, and then 1, 2 times this term here. I've written it out. These are in terms of cycles. This is the longhand notation, and we have the convention of going left to right, which I've described in the very first lecture in this playlist. So we start here, 1 to 2, then 2 goes to 2, so the net result is 1 gets mapped to 2, then 2 to 1, 1 to 3, so that gives us 2 to 3, and then 3 to 3, 3 to 1, and we get 3 to 1 here. So, and that's the same as in cycle notation, 1 to 2, 2 to 3, 3 to 1. So that's what we have here, and it turns out if you multiply 1, 2, 3 times these 2 elements in H, you're going to get the same set. Then we do the same for each of the other elements, and we get these 3 cosets, 3 different cosets. So when we do it on the right, the first one here, this coset is the same, but the other 2 are different. So you notice here, For example, when you have 1, 2 times H, you get this, and then when you have H times the cycle 1, 2, you get a different coset. This doesn't equal that, and there's other discrepancies here, which I'll invite you to have a look at in detail. But the main point was, in doing this example, was that the left and right cosets of a subgroup of a group G are not always the same. In fact, they're typically different. We have a third example of cosets. This is the dihedral group, which I talked about in the first lesson in this series. I've copied the table, the Cayley table for the dihedral group. So if you're not familiar with that, I would suggest going back to lesson 1. But what we want to show here is two different cases. First, we'll take H equals the set EB, and we'll compute the left and right cosets, which I've shown here. And you notice that of course the coset related to the identity is always you're going to get the same thing here, but the other ones are not equal. So if you have AH, for example, A times H, you get AAB, but then you have H times A, and you get A times BA. So these two are not the same, and you see there's other ones that are not equal also. For example, H times A squared and A squared H give you two different results. So the left and right cosets for the same element from G are not always equal when we take H to be EB. And if we take H to be the identity, A and A squared, actually the left and right cosets are equal in that case. And I went through and computed them here. You have only two cosets, and the left cosets, E, H, AH, and A squared H equal E, A, the identity, A and A squared, and that equals the cosets H times the right cosets, H times A squared, H times A, and H times E. So they're equal here, and then you get another coset, BH, ABH, and A squared B. Whether you multiply on the left or the right, you get this set here. Okay, so sometimes left and right cosets are equal, and sometimes they're not. The index of a subgroup, H within group G, denoted by this notation here, the index of H within G, is defined to be the number of cosets of H in G. And we have a theorem: if G is a finite group and H is a subgroup of G, then the index of H within G is just the quotient here, the number of elements in G divided by the number of elements in H. And I'll give you a link here to the proof. It's by a book I mentioned a few times now by Rothman. So I'll put the link to that in the information to this video. The case where all right and left cosets are equal for a given subgroup of a group is critical in the study of group structure. A subgroup N of a group G is called the normal subgroup of G if and only if for every G, small g, in our group G, the corresponding left and right cosets are equal. In other words, we have this property for every G, small g, within our group G. In terms of notation, we write it this way here. So subgroup we write this way if it's just a subgroup, and then if it's a normal subgroup, we have this little triangle notation if N is a normal subgroup. An equivalent definition states that N is a normal subgroup of G, and for every element G, small g, in our group G, and X in our subgroup N, we have that G, X, G inverse is an element of N. This is sometimes stated this way here. Excuse me, N equals G times N G inverse for every G an element of G. If G is an abelian group, then every subgroup N is normal. Since if X is an element of N and G is an element of G, we have this here, using this alternate definition. And then we can just invert the order, because we're assuming an abelian group in this case. Then, of course, the G times its inverse is just the identity, and we get X. And so that fulfills and that's X is in N, so that fulfills this property here. For example, H equals the identity A and A squared is a normal subgroup of D3, the dihedral group 3, that we saw that in the previous slide. You may want to go back to the previous slide and determine what are the normal subgroups in our dihedral group 3, D3. On this slide, we have two examples of normal subgroups. The first example is the special linear group. If you recall from my first lesson, that's a set of all n by n matrices over a given field, such as the real numbers or the complex numbers, such that the determinant is 1, which also implies that all the matrices are invertible. And then they're a normal subgroup within the group GLN, general linear group, of matrices of size n by n, all of which are invertible over the same field F. We're going to use the alternate definition, which I've copied down here at the bottom, for being normal. So N is a normal subgroup of G if for every G an element of G, X an element of N, G, X, G inverse is an element of N. So we'll use this definition of normal to prove that SLN is a normal subgroup of GLN. So we take any A, an element of our special linear group, and any B, an element of our general linear group, and then we take B, A, B inverse, and we take the determinant of that, and the determinant of a product of matrices is just the product of the determinants, this here. But we also know that the determinant of any matrix equals 1 over the determinant of its inverse. So this determinant of B inverse equals 1 over the determinant of B, so they cancel out. And the determinant of A is 1 because A is in this special linear group. So the determinant of this product here is 1, and that implies that B, A, B inverse is in our special linear group, and thus, using this definition here, SLN, our special linear group, is a normal subgroup. Then we have a second example of AN, the alternating group of permutations, is a normal subgroup of the symmetric group of permutations. And again, this was something I went over in the first lesson in this playlist. So the product of two odd or two even permutations is even. And that's because a permutation can be written in terms of a transposition, just the 2 cycle. And if you have an even number of 2 cycles, then you're an even permutation. If you have an odd number, you're an odd permutation. And then when you just, for example, multiply 2 odd permutations together, the number of transpositions is going to be even. And the same thing when you multiply 2 even permutations, the number of transpositions is even. However, if you take the product of an odd permutation with an even, then when you add up the transpositions, you're going to get an odd number of transpositions. So the product in that case is an odd permutation. So keeping that in mind, we want to again use this alternate definition of normal to show that AN is a normal subgroup within SN. There's 2 cases. We take this G, small g within G, and it can either be in AN or it can be in Sn but not an An. So there are two cases here. So G inverse would also be an even permutation. So that's an An. And then for any X in An, you have the product here of G inverse would also be even because it's the product of three even permutations. Thus, this product is in An. Then in this case here, if G is an Sn but not an An, that would mean that G is an odd permutation. G inverse is also odd, and then you get for any X in An, you have an odd times an even times an odd, and so when you add up the number of transpositions, you're going to get an even number, right? You have the two evens, the two odds, G and G inverse. That'll give you an even number, and then of course the X is going to have an even number of transpositions. So the product is again even, and so the product of these three is an An, and we've shown that this product is in our normal normal subgroup, in which case that implies that we have a normal subgroup, since in both cases we've shown the product Gx G inverse is in N. If H is a subgroup of G, and the index of H with respect to G is 2, then H is a normal subgroup of G. So let's take a look at a proof of that. And remember, this just means that there's the size of G is twice that of H. Since H is a subgroup, it is closed under group operation. Thus, X times H, X times every element in H, equals H itself for every X an element of H. This gives us one coset. And we know there's only two because of the index is 2. So there's one other coset, and that would be of the form A times H, where A is an element of G but not an H. If it was an H, we'd be back to this first coset. But since there's only 2, then we know that the left and right cosets have to be the same. And so we have this equality here. So from there we have two cases to show that H is normal. First case, G is not an element of H, in which case we have GH equals AH, this A that we've talked about up here, and that equals HA, and then that in turn equals HG. And that's true since AH equals HA, which we established up here, and G is an element of AH. And so we have, if we just multiply G inverse on both sides here, we have this here. And you recall that was an alternate form of the condition we needed to show that a subgroup was normal. But we've only showed it in this case here, where G is not an element of H. If G is an element of H, then we have GH equals H, that's from this here, and that equals HG, and then again multiplying by G inverse on both sides we get this here. So either way we have this property, and that implies that H is a normal subgroup of G. That gives us another way of showing that the A sub n is a normal subgroup of S sub n, since we showed in the previous lecture, the first lecture in this series, that the number of even permutations was equal to the number of odd. And so the index of AM with respect to the Sn is 2, and so that falls into this theorem here. The set of cosets in a group G form a group itself. This is known as the quotient group or factor group. We write it as G/n, where G is the containing group and n is the coset. So for quotient groups, the operation star is defined as follows. We have coset AN times coset BN, and that's the coset ABN. So we have closure. The identity is the identity from our group G times the coset. So we have an identity. Since an inverse exists for every A and G, G being a group, we have AN times A inverse N equals, by the definition here, A times A inverse N, which equals the identity times N. So we've basically proven that this quotient group is a group. And if N is abelian, then the quotient group is also commutative or abelian. We have a theorem here. If G is a finite group and N is a normal subgroup of G, then the index of this quotient group is just the number of elements in G divided by the number of elements in N. This follows from theorem 13, which we did a few slides back, since the elements of G/N are the cosets of G with respect to N. You can also form quotient groups from infinite groups, and I give you an example here. NZ, so in other words, all multiples of the integers by some other integer n. So we're showing it written out in long form here. Then the cosets would be this set here, and then 1 plus each of these elements, and then 2 plus each of these elements, all the way up to n minus 1 times plus each of these elements here. And then, of course, if you did n plus nz, you would just come back to this one here. So you have these n members of the group. This quotient group, z/nz, can be thought of as equivalent to a group of the remainders modulo n under addition. In the next few slides, I'll talk about what we mean by groups being equivalent. The idea of equivalent groups is formalized by the concepts of group homomorphism and isomorphism. On this slide, I'm going to define homomorphism, and then I'll get into isomorphism in the following slide. Two groups, G and H, you notice they have different operators, are homomorphic if there exists a function f from G to H such that for all x and y and G, the following holds true. F of x times y, using the operation from G, equals f of x times f of y, using the operation for H. The purpose of defining a group homomorphism is to create functions that preserve algebraic structure between groups. We have an equivalent definition of a group homomorphism here. The function f from G to H is a group homomorphism if whenever x times y equals z, using the operation here from G, for x, y, and z, an element of G, we also have f of x times, using the operation for H, times f of y equals f of z. Okay, so these two are equivalent. Let f be a homomorphism between groups G and H. Let E sub G be the identity of G and E sub H be the identity of H. Then we have that f maps the identity of G to the identity of H, and f maps inverses to inverses. So this is the structure preserving property of a homomorphism that I mentioned on the previous slide, or should I say properties. To prove this, first part, take any G, an element of G, then we know that we have E sub G times G equals G. Then we use the alternate definition of group homomorphism to get this equality here. Going from here to here follows from this. And then we can just multiply the identity times f of G, and this we get this equality here. But now we have two different things multiplied times f of G to give us back f of G. So E of H must equal f of E of G, which proves the first part here. The second part of the theorem has a very similar proof. Take any G, an element of G, then G times its inverse is the identity. Using the alternate definition of homomorphism, gives us this first equality here. And then this G times G inverse equaling this follows from this here. And then the fact that f of E of G equals E of H, that's what we proved in the first part. So now we have f of G times f of G inverse equals the identity in H, but inverses are unique. So we have that f maps G inverse to f of G inverse. In other words, inverses are mapped to inverses. So that proves the second part of the theorem. A key point regarding homomorphisms, for example from group G to H, is that they are only required to map into a subgroup of H. For example, the following mapping, we'll call it F, defines a homomorphism from the integers mod 3, so in other words 0, 1, and 2, to a subgroup of the dihedral group D3. Here's our mapping F. So we have 0, 1, and 2, and it gets mapped to the identity A and A squared. To prove that F is a homomorphism, we need to show this identity holds for every combination of X and Y. And I did it for just 3 combinations, and then I left the others to the listener. So I did it for 1 and 1, 2 and 2, and 1 and 2. And we don't know that this equality equals is valid yet, but we need to check it from both sides. So looking at it in this direction, f of 1 plus 1 equals f of 2, and f of 2 is a squared. And then f of 1 times f of 1 is a times a from here. Then that's a squared. So this equality holds. F of 2 plus 2 is f of 4, but 4 mod 3 is 1, and f of 1 is a. And then going in this direction, we have f of 2 times f of 2, a squared times a squared. That equals a to the 4th, which is a in the dihedral group for n equals 3. And then last one, f of 1 plus 2 is 0, because 1 plus 2 is 3, and that's 0 mod 3. And f of 0 gets mapped to the identity. Then going this way, we have f of 1 times f of 2, that's a times a squared. It's a cubed, but a cubed in the dihedral group is the identity. So again, we have equality for this one. And just to note, the D3, the dihedral group for n equals 3, has 3 additional elements, and there's no mapping from the integers mod 3 to those additional elements, but that's fine for a homomorphism. We only needed to show that this property held for all x and y in the integers mod 3. A homomorphism F from G to H, where G and H are groups, that is one-to-one, is called an embedding, i.e. the group G embeds into H as a subgroup. If f of G equals all of H, then F is onto, that's also known as surjective. So a homomorphism that is both injective and surjective is an isomorphism. The names of the elements in the two isomorphic groups may differ. They may also look different in terms of the Cayley diagrams, but the isomorphism guarantees that they have the same algebraic structure. When two groups, G and H, are isomorphic, we write it this way here. Instead of an equal sign, we have a little tilde on top of the equal sign. A simple group is a group whose only normal subgroups are the trivial group, the identity element, and the group itself. A group that's not simple can be broken into two smaller groups, the non-trivial normal group N and the corresponding quotient group G/N. This process can be repeated for finite groups. One can determine a cascade of normal subgroups known as a composition series. Stated more formally, if G is a group, then one can construct a series of the form shown here. You're starting with the identity and then progressively getting larger normal subgroups, each of which is contained in the next, until you finally end up with G, which is also a normal subgroup of itself. With strict inclusion, i.e. n sub I is a proper subset of n sub I plus 1. So in other words, proper meaning it's not equal to, it's somewhat smaller. And each n sub I is a maximal normal subgroup of n sub I plus 1. Further, each quotient group n sub I plus 1 slash n sub I is a simple group. The following theorem tells us that composition series for a finite group are equivalent. I have that on the next slide. The Jordan-Holder theorem states the following: the composition quotient groups belonging to two composition series of a finite group G are, apart from their sequence, isomorphic in pairs. So in other words, if we have the following two composition series for finite group G, so we talked about this on the previous slide, these are all normal subgroups of G, and each one of these is a normal subgroup of the next one. So if we have two of these, then T equals S, you have the same number of them, and all corresponding quotient groups are isomorphic. So n sub I plus 1 slash n sub I is isomorphic to m sub I plus 1 slash m sub I. And the proof is not simple. It's quite a long proof, but I have a reference for you to an article by Benjamin Baumschlag. So I'll put that in the information to this video in case you're interested. Okay, so that's the last slide in this lesson. I have one more lesson on groups, and that's about the classification of finite groups, which is a rather interesting topic, something that's finalized actually in the last several decades.